गुड आफ्टरनून टू ऑल ऑफ यू। सो आज हम लोग डी ऑर्बिटल्स एंड फोटो इलेक्ट्रॉन स्पेक्ट्रोस्कोपी फॉर ट्रांजिशन मेटल कॉम्प्लेक्सेस इसके बारे में थोड़ा सा पढ़ेंगे। सो विल ट्राई टू लर्न अबाउट दिस फोटो इलेक्ट्रॉन स्पेक्ट्रोस्कोपी ऑफ ट्रांजिशन मेटल्स और particularly these are photo electron spectroscopy becomes important in certain complexes where the d orbital is full। ठीक है, अगर आपको डी डी स्प्लिटिंग जानना है, डेल्टा नॉट वैल्यू जानना है और उसमें डी ऑर्बिटल में डी डी ट्रांजिशन पॉसिबल ही नहीं है क्योंकि उसमें इलेक्ट्रॉन्स पूरा डी सबशेल फुल है, वैसे केस में ये काफ़ी इट इज़ वेरी हेल्पफुल द टेक्निक because it relies on an entirely different mechanism, ionization of electrons from the completely filled energy levels. So if you compare the two energy you will get the value। मतलब अगर ध्यान से अगर आप फॉलो करेंगे, so there are two cases where this will be important. One is when the d orbitals are full and strongly bound and they are full and not participating in the bonding to that extent, only small effect due to bonding will be there. So these examples you will find in mercury 2 compounds, gold, cadmium and later transition metals compounds, 4f electrons in lanthanides. So in all such cases d orbitals, this technique would be very helpful in knowing the when you want to know this DD splitting or anything like the orbitals, energy of the orbitals when you try to locate this. So this kind of thing is important. Second situation, in which in transition metal complexes when the d orbitals are outermost, so they give out bands at lowest ionization potentials, sometimes at very low potentials. So these complexes are, so typically if I simplify it for you, when you have zero oxidation state in complexes where metal is in very low oxidation state, there also this kind of thing will be very helpful. So याद होगा हमने फर्स्ट सेमेस्टर में भी जब डिस्कस किया था डाइबेंजीन chromium. So in those kind of compounds where zero oxidation state or negative oxidation state of the transition metal is there, वहाँ पे भी ये helpful. So this technique is helpful. So in both these situations that we are discussing, two situations, d orbitals are only weakly involved in bonding. So a common term that we can use here is the d orbitals almost negligibly involved, weakly involved in bonding. There this kind of technique, photoelectron spectroscopy, is useful. So when they are not involved in bonding, they give distinct bands in the photoelectron spectra which can be easily recognized and assigned to that d orbitals. So in other cases the d orbitals are heavily suppose the cases where it is heavily involved in bonding, mixed states would be found and slightly difficult, इतना easy नहीं होता interpret करना फोटो इलेक्ट्रॉन स्पेक्ट्रम. बट ये जो केसेस मैं बता रहा हूँ जहाँ पे d ऑर्बिटल फुल है या मेटल ट्रांजिशन मेटल जीरो वैलेंट स्टेट में है, उन सारे केसेस में इसमें इजी होगा. So So UV PES usually done in gaseous state. So most volatile transition metal complexes are formed with which ligands? अगर आपसे पूछा जाए most volatile transition metal compounds will always be found with cobalt or PF3 as the ligand. Okay, so what is the so special about these CO and PF3? They are both have capability to donate electrons through sigma bond and accept electrons from the metal through pi bond. So this electron donor and donating and electron accepting sigma donor and pi accepting ability is there with these ligands. Okay, so the back donation, the stability of the complex is crucially determined by depends on what the back donation is very important, and how well it is accepted into the pi star orbital of the ligand. That determines the stability of the so this is a cooperative effect, that जितना चार्ज सिग्मा से जाएगा सिग्मा बॉन्ड के थ्रू सिग्मा डोनेशन स्ट्रांग होगा उतना बिल्डअप ऑफ चार्जेस मेटल पे होगा एंड देन मेटल विल आल्सो try to restore electron neutrality and give back electrons to the thing. So utna hi. So that's why we say sometimes that this cooperative effect. But what we want from the ligands is that they must be sigma donors and good sigma donors, good pi acceptor properties. And accepting pi electrons is the most important for the stability. Accepting wala part जो है वो ज़्यादा important है. So if you analyze photoelectron spectrum for these compounds, uh, it is you can tell which one is better pi acceptor. ये फोटो इलेक्ट्रॉन स्पेक्ट्रोस्कोपी से पता चल जाता है कि आउट ऑफ CO और ट्राइफिन फॉस्फोरस ट्राइफ्लोराइड इसमें से which one can act as better pi acceptor, which one is better pi acceptor, पूरा एविडेंस के साथ आप बता सकते हैं. So this is a very special technique in that sense. No other technique can tell you so easily about the pi accepting capability of a ligand. So how do we do it? We just let's see. So all these compounds that are formed with COP3 all are in low spin that we know. So such metals in the second half of transition series are found to have formed better complexes with these ligands, and so in these metals in second half what you have several occupied d orbitals, relatively high energy, from which donation can happen. So so जो एक क्वालिटेटिव आइडिया है उसको एक मतलब एविडेंस के फॉर्म में ऑब्जर्वेबल इफेक्ट के फॉर्म में कैसे लाया जाता है वो हम देखने जा रहे हैं. अभी तक हम थियोरेटिकली मॉलिक्यूलर ऑर्बिटल थ्योरी डिस्कस कर रहे थे इन only the conceptual manner, but the evidence of that sigma donation pi acceptor properties you will get through this. So so the orbitals that are involved is the filled d orbitals, empty s and p orbitals, empty s and p orbitals of the metal, full sigma and empty pi star orbitals of the ligand. So these are the orbitals involved. PF3, imagine PF3 में क्या होगा, lone pair of फ्लोरीन, लोन पेयर ऑफ फॉस्फोरस, और फॉस्फोरस के थ्रू आपको डोनेशन होगा. and so the compound formation should cause stabilization of both the ligand sigma orbital. So what we expect कि sigma orbital जो है sigma donation जो हो रहा है वो those orbitals of the ligand and the metal d orbitals both must have, after the formation of the donation of the electron, sigma donation and back donation, they get lowered in terms of energy उनकी कम होगी तो वो स्टेबल कंपाउंड बनेगा. Okay, so let's see this graph first, then we'll try to understand. PF3, pure PF3. First graph that you see, PF3 का है. So ligand. So what do you see here? One, there is this is for PF3. Then next one is graph is for MO PF36. So and the third one that you see is MO CO6. सो मोलिब्डेनम के दोनों कंपाउंड है नीचे, ऊपर एक लिगेंड है जो PF3 वाला है. सो PF3 लिगेंड was PF3 in metal complexes. So you can see here there are certain things which you can easily point out. PF3 का जो ऑर्बिटल्स है और यहाँ पे जो आपको दो ऑर्बिटल्स दिख रहे हैं at the lower energy side, these are the d orbitals of metal. Metal का जो d orbital metal is electropositive, it is easier to take out electrons. So when you are looking at the complex, remember it must be some metal orbital which is ionizing early. The electron ejection is easy. So these are the molybdenum d orbitals, lower energy side, lower ionization energy, PF3 versus CO6. These are the between 8 and 10 electron volts. दूसरी साइड at another extreme, look at the another extreme, another दूसरी छोर पे क्या है, at the another extreme of the scale, in the graph what you find, the two things, first two graph, compare the two, the blue dots. So these are PF3 orbitals which are unaffected, which do not take part in bonding. So ये most likely जो फ्लोरीन के जो bonding orbitals, non-bonding orbitals हैं वो. So something that doesn't take part in bonding, you can see the values around 16, 18. So this is remains unaffected. You can clearly see that. So these हिंट आपको मिलना शुरू हो जाता है कि क्या अगर ये दोनों स्पेक्ट्रम दिया है तो आप कंपेयर कर सकते हैं. एक जो नया अपीयर हुआ डेफिनेटली मेटल की वजह से होगा, और जहाँ पे जो चेंज आपको दिख रहा है, दिस वन, व्हाट आर दिस? So F lone pairs and PF bonds, that was the blue one that we saw, and this one that we are seeing is the phosphorus lone pairs, and then this phosphorus lone pairs which was individually PF3 में जो अकेले में था, it splits into two in the octahedral symmetry. So T1U EG A1G. So आप इमेजिन कीजिए 6 phosphorus atom PF36, they are arranging themselves around the molybdenum atom in a octahedral fashion. So the orbitals, the lone pair, 6 lone pairs are required, arranged in this form, and that they are classified T1U 3 2 1. So degeneracy of the system, you know, T1U का मतलब triply degenerate, 3 2 1. So intensity ratio you also expect 3:2:1. अब देखिए उसी रेशियो में आ रहा है. Sorry, you can clearly see this thing, that this particular thing is 3 2 1. 3:1 के रेशियो में आपको दिख रहा है. सो दिस वन इज डेफिनेटली द फॉस्फोरस लोन पेयर, जो 12 से 14 के बीच में था पहले, वो अब स्प्लिट कर गया है 3 में, and overall intensity is same, and now the individual intensities is in the ratio 3:2:1 T1U EG doubly degenerate A1G single. So accordingly, तो ये कैसे हो रहा है, ये थोड़ा सा आप let me take you to some. So ये आपको याद होगा जब हमने शुरू में डिस्कस किया था लीगेंड फील्ड थ्योरी, फर्स्ट सेमेस्टर में उतना समय नहीं मिला था जो काफ़ी डिस्कस करना था, जो नहीं हो पाया होगा. But if you remember what we had discussed, that when we organize these things, so this was the ligand field theory. So just little bit of background is needed. So when you combine the orbitals of like symmetry to make molecular orbitals, तो कैसे करते हैं? So molecular orbitals in a donor atom जो होगा ligand का p orbital होगा approaching the metal to form a sigma bond. dx dy dz orbitals are not of for sigma bond. So along the axis कौन से काम आएंगे? dx square minus y square dz square px py pz. So these are the orbitals on the and s orbitals. So these are having correct symmetry to form the sigma bond. Okay, so these are the metal orbitals which can be used for formation of sigma bond. इसी तरह से जब उसकी जब इसको हम वर्कआउट करते हैं, रेड्यूसिबल A1G T1U EG आता है, यही अभी डिस्कस कर रहे थे हम लोग. सो ये सिग्मा बॉन्डिंग के लिए यूज होगा. तो मेटल के ये ऑर्बिटल्स यूज होंगे dx dy dz dx स्क्वायर माइनस dz स्क्वायर pxy एंड s ऑर्बिटल्स. ओके, so it is a T1U symmetry A1G, and s orbital have A1G symmetry, px py pz, and T1U having this kind of symmetry. T1U symmetry में ये 3 आ गया, px py pz, और EG symmetry में dx. so octahedral framework में ऐसे हमें सारी चीज़ें मिल जाती हैं. So these were the things that we discussed earlier. Atomic orbitals that combine 6 bonding molecular orbitals are filled by ligand electron pairs. So imagine ये सारी चीज़ें अभी हम लोग डिस्कस करेंगे. ये पहले से अगर आपके दिमाग में है तो it becomes easier what we are discussing. वहाँ पे नहीं तो फिर ये पीछे की चीज़ें आपके पास, if you have forgotten, then it becomes very difficult. So on the metal side you have s orbital, p orbitals, 3p orbital with T1U symmetry, A1G symmetry, and the one with EG, 2d orbitals of which have electron densities along the axis. So सारे orbital जो metal के हैं जिसमें electron density along the axis है, वो सारे orbitals यूज हो सकते हैं to form bonds with ligands, x minus ligands over here. So p अगर सपोज सिंपल फ्लोरीन है, क्लोरीन है, ऐसा कुछ है, तो उसमें जो सारे ऑर्बिटल्स हैं वो अराउंड द मेटल दे विल बी अरेंज्ड इन दिस 3 डिफरेंट सिमेट्री T1U EG A1G. सो सारे p ऑर्बिटल्स मिलके ऐसा एक बनाया जाएगा 6 bonding molecular orbitals and 6 bonding MOs and 6 anti-bonding will be formed. Okay, so ये bonding anti-bonding. So 3 p ऑर्बिटल, 1 s ऑर्बिटल और 2 d ऑर्बिटल, ये सब मिलके आपका 6 का 6 कैसे बनता है वो आपको यहाँ पे एंटी बॉन्डिंग है वो. So this is the thing. So 2 EG star orbitals, anti-bonding orbitals are lowest energy anti-bonding orbital. So ये यहाँ पे ऐसे आएगा. और जब So this is the case when you don't have d electrons from the metal ion will fill the T2G and Eg set here, and this one is the delta knot. So Eg star is raised up in energy. This is anti-bonding orbital in terms of molecular orbital. Eg bonding is here. So according to symmetry, we combine the orbitals and we get the so separation between the this T2G level and Eg star is your delta knot. This is the simple case. Now with cases where back bonding can happen, orbital energies, just a moment, not this one. So accordingly, when you have ligand orbitals, then when you have to organize this thing, so this is Txz T1u, so T1u matches with Px Py Pz 5 bonding, but so in this kind of orbital, what happens when you have sigma donor orbitals are there. This is the diagram of Cn minus, not you already know. So what happens in these cases where we have metal back bonding thing, pi acceptor back bonding thing is happening. So in addition to that difference, T2G, which was not T2G was here, Eg star was raised in energy, and now if you have orbitals of suitable symmetry, T2G, so this will have lateral overlap. So T2G empty ligand group on the metal, T2G is here. So ये अगर एडिशनल चीज़ें जो पिछला हमने देखा उसमें T2G के करस्पॉन्डिंग सिमेट्री का कोई ऑर्बिटल था नहीं मेटल के लिगेंड के पास. अगर लिगेंड के पास सुटेबल एनर्जी और सुटेबल सिमेट्री T2G वाली सिमेट्री का ऑर्बिटल होगा, then this one is possible. And if metal already has electrons in the T2G, they will go in this thing and this one is your delta naught is increased. So अब आप जब T2G और EG का गैप ये करते हैं तो ये आपको यहाँ पे दिखता है. So the anti-bonding orbital T2G star, it has all the character from the 3 new anti-bonding orbitals are formed. So this one is what we were talking about. We say that it has almost the same character as that of the ligand. ligand के ऊपर जो जिसमें कि बैक डोनेशन होगा मतलब okay, so the new Eg star MOs of formed molecular orbitals from the sigma bond. So this Eg star is here and from sigma bonds only this was the situation, and now with pi acceptor ligands this is how the energy is raised, because now you have orbitals of T2G symmetry or empty ligand group orbitals with which such bonds can be formed. So Cn minus was one of the examples that we have discussed earlier, but here in the context of PF3 similar situation arises. So it is a transfer of electrons, so this kinds of thing is happening. So you have orbitals which just a moment. So this is the situation, bonding situation that we were discussing. Pi acceptor ligand, this is where we are currently, and there is increase in. So this is the back bonding scheme, pi to metal to ligand back bonding. This is what we call acceptor ligand. So this is, so once you have this picture in mind, you can go back and then talk about the PF3 case. So we are discussing the molybdenum. So at the lower side, lower ionization energy, what we have is molybdenum d orbitals. It is easier to take away electron from the d orbitals, metal d orbitals, and so it appears as very low ionization energy. See the scale, 8 lowest here and highest on this side. So we first, what we did, we first analyzed दोनों जो छोर पे at the two extreme positions, whatever band you are getting, you first analyze, try to analyze them. So these are the bands which are, one belong to the purely metal d orbitals, and then another set is for the PF, the blue one that we see, the fluorine lone pairs of the PF bond, and then the phosphorus lone pair which actually participates in sigma donation. This is in an octahedral situation, this gets split into 3 to 1, T1U EG, T1U EG, and A1G. So these three things, so these three appear in that ratio also. So you can clearly see this happening, that how in octahedral symmetry the 6 phosphorus lone pairs, the orbitals that approach the central metal, they form ligand group orbitals. So these are the ligand group orbitals which of 3 different symmetries, T1U, EG and A1G, which bind with the metal. So this we can see clearly over here. And then, so what you see here is a few things, observations which you should also note. We have seen 2 complexes of molybdenum, one of carbonyl, one of PF3. What we find, the band with the lowest ionization energy in the spectra is, it shifts only by 0.7 electron volts when the ligand is changed. So look at this only, so this one is here, and so this, the change in these two peaks, so it changes by only 0.7 electron volts when the ligand is changed. And so the one which changes with must be is, so जिसमें सबसे कम चेंज हो रहा है, डेफिनेटली वो मेटल का डी ऑर्बिटल होगा, ठीक है, क्योंकि मेटल का डी ऑर्बिटल्स which is completely full, it is not participating in the bonding, and so it should be least affected. So all the complexes of low spin, all of the 6 d electrons are in the T2g orbitals, and the d electron bands. so low spin complexes are 6, that d sorry, the 6, so that means T2g 6 electrons in this T2g set, and the d electrons ionization appears as a single band. So we expect a single band when there is all the electrons of d orbitals are only in either T2g set or EG set. So here EG levels of the d metal is empty and only T2g is occupied. It is a low spin complex. So this is the situation. So a single band, तो उन सब की एनर्जी बराबर ही होगी. So if you're trying to take out any one of those electrons which are in the degenerate state, so imagine you have d orbitals EG and T2g, six electrons. So ionization energy lowest for this T2G set. So you are ionizing the electron, taking out electron completely away from the metal. So this is the lowest ionization. So what we see at around the 8 to 10 electron volts, that is the lowest ionization energy is the for the d orbitals, and a single band will appear. Eg में तो कुछ है ही नहीं, so d के लिए आपको एक ही मिलेगा. So this is the one thing that we observed, and this it was in the previous graph. Then what next? What other things that you have just observed? So electronic configuration of atomic molybdenum and that of molybdenum in the complex are so different that the d electron ionization. So metallic. So we have not compared the metallic d orbital, of molybdenum, atomic molybdenum, and the molybdenum in complexes, because that is very different and it will be very difficult to analyze here. But what we have compared, PF3 or the ligand alone and the complex with with the metal of the PF3 with the molybdenum. So these two comparison we have seen. What we have what we see that so metal d orbital ion, if you compare the metal d orbital ionization potentials, so एक बार फिर से let's go back to the graph. What you find, if molybdenum d orbitals, so it is easier to take out electron in CO. It is difficult to, the ionization energy in case of this is slightly higher. In case of PF3, so what you see clearly here, ionization energy for d orbitals higher in case of for PF3 कॉम्प्लेक्स. जो PF3 वाला कॉम्प्लेक्स है मोलिब्डेनम PF3 6 कॉम्प्लेक्स है, इसके लिए जो आयनाइजेशन एनर्जी है वो ज़्यादा है, मतलब इलेक्ट्रॉन्स को निकालने में. सो इट टेक्स अ ग्रेटर एफर्ट to take out electron from molybdenum if the ligand is PF3. If the ligand is PF3, it is difficult to take out electron from the molybdenum d orbitals, which also means, इसका ये मतलब हुआ कि PF3 is able to stabilize the complex much better. और ये जो complex है, so this is the proof that the PF3 is acting as a better pi acceptor. So that is clearly you can see from the previous graph that PF3 causes greater stabilization because the metal d orbitals ionization potential is higher as compared to the other complex with carbonyl, and so it seems to be better pi acceptor than Cu. So जो आप theoretically पढ़ते थे कि PF3 should be better pi acceptor, उसका proof है. This is the proof of experimental evidence of PF3 being a better pi acceptor than Cu. In the high ionization potential regime, 15 to 20, what we find, there is no difference between the photoelectron spectrum of PF3 and its molybdenum adduct. So that means it is talking about this thing, high energy side between 18 this side 18 to 20. So this remains unaffected. ये वाला जो part है PF3 alone and PF3 in complex, when you compare the higher energy side, you find that it remains at the same position. Position has not changed. Position is same position, unaffected. So these are the something, इससे ये idea मिलता है कि ये कुछ वैसे orbitals हैं, these are certain orbitals which are not participating in the this complex formation, the bonding, वो unaffected रह रहे हैं. So that idea tells you that this must be due to the fluorine lone pairs which are not participating in the sigma donation process. और इस वजह से, so that is one indication. So on that side, on the 15 to 20 electron volt, you have the one that remains unaffected is clearly the in fluorine lone pairs on the PF bonds. Okay, phosphorus lone pairs are getting is directly involved in the bonding, and their potential you can see it is changing. So जो involved है उसका change हो गया है. So something that is involved, so amongst the ligand orbitals, that is ligand orbitals that is directly involved in bonding, you can see that clearly the ionization potential has changed. It splits the profile of the peak profile has changed in the appearance. एक जो था वो अब 3 में स्प्लिट कर गया है, 3:2:1 के रेशियो में, T corresponding to T1U E1G EG and this A1U A1G, sorry. So these are the complex forms. So then what you also observe that at 12.2 electron volts in the PF3 spectrum, lone pairs are located, lone pairs of phosphorus used in sigma donation, and that they, so these lone pairs when arranged in octahedral symmetry, they become this kind of molecule T1U, EG and A1G. So these three orbitals, these three set of orbitals, there are 6 orbitals, ligand lone pair orbitals in 3 categories, one having this T1U symmetry, EG symmetry, 2 of them having EG symmetry and one having A1G. They are stabilized by the interaction with molybdenum P, D or S orbitals. So this is one thing that we can see. So what we see here, एक बार फिर से, so this one is stabilized, this one is particularly so this one is getting stabilized by interaction with, so this was the P lone pair orbital containing orbitals which is getting stabilized by interaction with D, P and S orbitals on molybdenum. So this one is clearly you see here happening over here. Okay, so these are the explanation of what you have observed. So sigma donation occurs and this one is stabilized. The 3 bands in molybdenum, they are identified by their relative areas and as given in this. So all of them, all the 3 orbitals are stabilized relative to the lone pairs of free PF3. Free PF3. So did you see this? आप ध्यान से देखिएगा, stabilized हम कैसे बोल रहे हैं? How, looking at the spectra, how can we say that something has been stabilized? इसी का जो ionization potential है, look at the ionization potential, how difficult it was to take out electron. Now this one is also slightly shifts to the higher energy side. These all are shifted towards higher energy side. That means now it is much difficult to take out the electron, the lone pair of ionization of lone pair phosphorus lone pair has become more difficult. ठीक है? This clearly shows that it has become more difficult. It has shifted to higher ionization energy values, and so it is being stabilized by sigma donation, forming sigma bonds with other suitable with the metal orbitals of suitable symmetry. So metal के जो s, p और d orbitals हैं उन सबको जोड़ के आप कर सकते हैं. So that is one thing that we see. And one more thing. So in the MoCO6 spectrum, only one band in the sigma bonding region can be seen, and that is represent the T1U orbital, 13.2 eV. So where is 13.2? This one, this is what we are talking about, 13.2. So here only one band is seen instead of three. You are getting in this region. So carbonyl. Okay, so that one is the only T1U orbital is available, and that is overlapping with this. So बाकी जो set है उसमें नहीं है. The other sigma bonding orbitals presumably overlap the part of spectrum and attributed to ionization from orbitals located in the CA molecules. So बाकी सब थोड़ा सा overlapping में चला जाता है. So only the T1U orbital is seen. One more thing, so this is another example of application of photoelectron spectroscopy to nickel complex, NiCO4 carbonyl complex and PF3 complex. Two complexes have been compared. Again, what you have to see, find the nickel 3D orbitals. So so you can see here so these are two tetrahedral complexes. So ध्यान दीजिएगा, अभी हम लोग octahedral complex की बात कर रहे थे, and the next example that we are discussing is the tetrahedral complexes of nickel carbonyl and nickel PF36. So here also what you see, ये E and T2 इन दोनों के corresponding. So अब जो tetrahedral state में निकल so what is the number of electrons in d orbitals? 3d8. So you have electrons in T2 and E. It is always so in this case both the electrons are removed from T2. So ionization energy, so electron taken out from the T2, ionized from the T2 orbital, electrons are ionized from the E orbital. So both two peaks are appearing. So here also you have nickel 3D, nickel 3D orbitals. Okay, and then so nickel 3D orbitals यहाँ भी है, और इधर वाला portion क्या है? So this is the 16 to 18. So this one is fluorine lone pairs which do not take part in the bonding. Okay, so PF bonds. So what we find here, what is in the spectrum that you find? So both are zero valent. Nickel is in zero valent state, zero oxidation state. It has a complete D shell, both the T2 and E orbitals. T2 orbitals and E orbitals are full of electrons. The first band what we found splits into two, so corresponding to ionization from T2 orbital and E orbital. So 3:2, approximately the ratio is 3:2. The splitting between the states. So strength of the ligand field is about the same in PF3 and CO complexes. So splitting between the two states is same, uh, the extent to which the splitting has occurred. So दोनों में ये भी, ये जो आप देख रहे हैं, ये T2 के लिए था और ये E के लिए था, और इन दोनों के बीच का एनर्जी जो आप निकाल लेंगे. सो इफ यू आर ऑब्जर्विंग इट केयरफुली, if the separation between two is giving you the delta T. So energy, energy gap of DD splitting that you have found from the spectrum, electron spectrum. It is when the electron D subshell is full, you can still find the DD splitting by using this photoelectron spectroscopy. ठीक है, तो ये चीज यहाँ पे इम्पोर्टेंट हो जाती है. सो but once, what we again see, अब इन दोनों कॉम्प्लेक्सेस में निकल के केस में भी हम लोग देखें, look at the nickels, metal orbitals. So with PF3, the ionization potential has a value which is on the higher side. ध्यान से देखिए इसका स्केल x एक्सिस पे कितने पे जा रहा है. Sorry. So what you see here, this is the T2, this is T2. ठीक है. So this is around, with PF3 it is 8 9 point something, very close to 9.5, 9.6, something like this. But here it is, T2 is appearing at so ये चीज ध्यान दीजिएगा. जो हाँ, लुक एट द स्केल, एक्स एक्सिस पे जो स्केल है आयोनाइजेशन एनर्जी का, कार्बोनिल के साथ सेम निकल, यहाँ भी निकल ही है, लिगेंड का डिफरेंस है, ज्योमेट्री टेट्राहेड्रल ही है. सो PF3 वर्सेस कार्बोनिल, you can see that the metal d orbitals, T2 का जो ionization energy है वो around, so less than 9, here it is something very close to, ये 9 eV है, ये 9 से ज़्यादा है यहाँ पे. so दोनों उसी तरह से E का भी देखिए, जो E वाला ऑर्बिटल है मेटल का, उसका वैल्यू वेरी क्लोज टू 10, and in the case of nickel carbonyl complex, but in case of PF3 it is higher, much higher than 10, it is here above 10. So ionization energy of d orbitals shift to higher values, they are of much higher, slightly higher in case of PF3 complex, the as compared to carbonyl complex. So that again tells you that PF3 complexes are more stable. So they, this stability addition, बाकी सब तो कुछ बदला नहीं है, ligand बदला है. ligand में क्या बदला है, the capability to accept electrons. So again it shows that PF3 is a better pi acceptor than Cu. So this comparison again tells you PF3 is better pi acceptor than Cu, and that's why the d orbitals shift, the ionization energy of d orbitals have shifted, the same metal d orbital is shifted to higher value. ठीक है, मतलब जब वो PF3 के साथ बॉन्ड बना हुआ है, when coordinate covalent bond is formed, it becomes much difficult to to take out the electron from d orbitals. जब कार्बोनिल के साथ मेटल का बॉन्ड बना है, in that case it is much easier to take out the electron. So इसका मतलब क्या हुआ, PF3 is more stabilizing, and the difference in strength is attributed to the pi acceptor ability. So So this is the evidence again with the second compound, एक molybdenum वाला octahedral में था और ये PF3 का sorry ये tetrahedral complex है. So this kind of analysis tells you about this. Rest of the analysis is same. The orbitals of fluorine, lone pair orbitals of fluorine that doesn't take part in bonding, उसका बदला नहीं कुछ भी. जो पार्टिसिपेट किए, इंटरैक्ट किए, उनका चेंज हो गया है आयनाइजेशन पोटेंशियल. So we have seen the d orbitals getting stabilized, and so the PF3 lone pair uh, that also getting stabilized. So lone pair donation वाला कौन सा था? ये वाला एग्जाम्पल था. Okay, so that is lone pair donation. Okay, so that is the photoelectron spectroscopy for transition metals. Uh, so so what we find here, these complete illustrate a generalize. So now we can generalize based on these two discussions of tetrahedral and octahedral complexes. Metal complexes, photoelectron spectra of metal complexes is divided into three regions. Three regions हमने अभी भी किया है. एक, the metal d orbitals. Two, the metal to ligand bonding orbitals. Three, pure ligand orbitals. Three regions. So pure ligand orbitals not affected, metal d orbitals affected by this thing, metal to ligand bonding orbitals affected by this. So ये सारी पैटर्न्स हमने देखे हैं. So थ्री रीजन्स में डिवाइड करो, उनको एनालाइज करो, यू विल गेट टू द this aspect of how the metal d orbitals have been stabilized, which ligand is causing more stabilization. All these things can be understood in this case. So when the uh, two sets of T1, T2G and EG both are occupied by electrons, you cannot have a simple DD transition. और आप DD splitting इतनी आसानी से नहीं निकाल सकते. But अगर आप using UV with absorption spectra, you can't do that because no excitation from T2G to EG is possible if the electrons are already present. But you can always do photoelectron spectroscopy, ionize the electron from both the levels and calculate the DD del value. ठीक है. So that's all for the UV spectroscopy, UV photoelectron spectroscopy. Next, in the next class tomorrow morning, we will discuss XPS, the photoelectron spectroscopy. Okay, so little bit on photoelectron spectroscopy, and that will finish the this topic. So I stop here.